Let's discuss Unit 4 solutions. Let R with attributes A, B, C, D be a relational schema with the following function dependencies. They have given 4 functional dependencies. The decomposition of R into A, B, B, C, B, D. So if you take A, B, C, D all together to be a single table in the context of relational database, just imagine R is decomposed into 3 other tables. The first table will have the attributes A and B, the second table will have the attributes B and C, while the third table will have the attributes B and D. So this is how they have decomposed the relational schema. A set of options have been given and it is based on two concepts. One is lossless join and the other one will be dependency preserving. Let's first discuss what is a lossless join. If there is a relation R and it is decomposed into two other relations, namely R1 and R2. Let's take this for an example. The decomposition of R into relations R1 and R2 such that if we perform natural join of R1 and R2, it will return the original relation R. So this is called as lossless join. So let's take R1 to be A, B, R2 to be B, C, and R3 to be B, D. So let's perform a join here. So when I join R1 and R2, I will get A, B, C attributes. So when I join A, B, C relation with R3, I will get A, B, C, D. So all the attributes are covered here. It means this will be a lossless join because even if we decompose the relation R into 3 other relations, when we perform a natural join of all these 3 relations, we ultimately end up getting the original relational schema. So this has a lossless join and whichever option say it does not give a lossless join will be removed now. Now we have to check whether this decomposition is dependency preserving or it is not preserving. What is dependency preserving? When we decompose a relation into smaller relations, we preserve the functional dependencies between the attributes. Let's take the first relation A, B. So is there a functional dependency from A to B? Yes, we have. So this relation is fine. Then we'll take the second relation B, C. So do we have a functional dependency? Yes, it is existing. So we have this FD. Let's take relation 3. It is B, D. Taking these two into consideration, from B I will be able to determine C and from C I will be able to determine D. So in this way, all the functional dependencies are preserved even when the relation R is decomposed into R1, R2 and R3. So it is also dependency preserving. In this aspect, we are ruling out option number 2. Option number 1, the decomposition of R into these 3 relations gives a lossless join and it is dependency preserving. We mark option 1 to be the right answer. Next question. A B tree used as an index for a large database table has 4 levels including the root node. If a new key is inserted in this index, then maximum number of nodes that could be newly created in the processes. Considering all nodes are completely full, this means every node has n minus 1 key. So if a new key is inserted, then two things will happen. At every level, there will be a new node created. Level 1, level 2, level 3 and level 4. And the second point will be in the root level. Root node will also be broken into 2 parts. So for 4 levels, we will have 4 nodes. And at the worst case, if the root node is breaking into 2 parts, we will get additionally 1 node. So totally, we can have 5 new nodes at the maximum. The maximum number of nodes that could be newly created in this process will be option 1, 5. Next question, consider the following statements. It is all about 3NF, BCNF and 4NF. When will we say a table is in 3NF? when the transitive dependencies are eliminated, the relation will be in third normal form. When will we say it is in BCNF? A relation must be in 3NF, and for a functional dependency X determines Y, X must be a candidate key or a super key. You can also take the other way. If Y is going to be the prime attribute, then X cannot be non-prime. So this will be the case of BCNF. A database design is in BCNF if each member of the set of relation schemas that constitutes the design is in BCNF. This is actually true. Next statement, a BCNF schema can have transitive dependency. Transitive dependencies are eliminated in 3NF. If it is already a 3NF, then a BCNF schema cannot have transitive dependency. So in this case, we mark B to be false. Once we conclude that B is false, whatever option involves B will be ruled out. From this we can mark option 4, A, C and D only will be the right answer. Now we will just check C. It is always possible to obtain a 3NF design without sacrificing a lossless join. There is a statement supporting this. They say it is possible to get third normal form without sacrificing lossless join or dependency preservation. This is also true. If we don't eliminate all transitive dependencies, we may need to use null values to represent some of meaningful relationship. So this is an additional point added to the C statement. Next statement, there are multi-value dependencies in 4NF. In second normal form, we eliminate partial dependencies. In third normal form, we eliminate transitive dependencies. In that case, multi-value dependency can be removed by 4NF. But when you get on to the explanation or definition of 4NF, there is a point stating no non-trivial multi-value dependencies other than candidate key. No important multi-value dependencies other than candidate key should be there. So in other terms, we can say this builds on BCNF. So from 3NF we go for BCNF, and from BCNF we go for 4NF. This builds on BCNF but must not contain more than one multi-value dependency. Actually, multi-value dependency will create redundancy. That's why they are trying to remove it in 4NF. So that one multi-value dependency might be because of this candidate key. So here there are multi-value dependencies in 4NF. From this statement we can say D is true. Next question. Given below are two statements. Which of the following concurrency control protocol ensures both conflict serializability and freedom from deadlock? Serializability is a term where every event will be occurring in some sequence or in some order. They have given two statements. First statement is about two-phase locking and second one is about timestamp ordering. Two-phase locking is based on locks and deadlocks may occur. When the term says it may occur, freedom from deadlock does not apply for two-phase locking. Though deadlocks may occur, it ensures conflict serializability. In this case, two-phase locking will not be the protocol that ensures both the things. So statement 1 will be false. Next is timestamp ordering. This will be based on timestamps and this ensures both conflict serializability and freedom from deadlock. So statement 1 is incorrect but statement 2 is correct. Option number 4 will be the right answer. So they have given in two-phase locking that deadlocks may occur. So what will be the step that will be taken is cascading rollbacks. Next question. Which one of the following is not a part of asset properties of a database transaction? A stands for atomicity, C stands for consistency, I stands for isolation and D stands for durability. So option number 4, deadlock freedom will be the right answer. It is not a part of asset property. Next question, let R A B C D F be a relational schema with following functional dependencies. So they have given few dependencies and they are asking which of the following is a key for R. Every option will be denoting a key. We have to find which is the correct key for R. So we will evaluate every key and find whether we are able to get all the attributes of relational schema. So let's start with CD. So from CD, I will be able to take the attributes C, D. Are there any functional dependencies starting from C? Yes, we have C derives F. So from C derives F, I will be able to find F. There are no dependencies with D. So only 3 attributes can be found. Let's take the second option, EC. Basically, we can find E, then C. From C, I can find F. It holds this. From E, I can find A. So E determines A. With EC together, I can find D. So D is also added here. And then A determines B. Using this, I can find even B. So all the 6 attributes are covered. Let's check the other 2 options, though we know option 2 will be right. AE. From AE, I can find AE. From A determines B, I can find B. E will determine A again. So I don't have C here. So it will stop with these 3 attributes. Next we have AC. So basically we can find AC. From A I can find B. From C I can find F. So the only key that will be able to give all the attributes will be EC. Option number 2 will be the right answer. Next question. Which of the following scenario may lead to an irrecoverable error in a database system? A transaction writes a data item after it is read by an uncommitted transaction. Here we have an error. First we'll see what are the statements that produces error, then we'll find which is irrecoverable error. A transaction reads a data item after it is read by an uncommitted transaction. So this operation is also read by uncommitted transaction and this is also read. This will not give you any issue, so no issues will be there. A transaction reads a data item after it is written by a committed transaction. Once it is a committed transaction, when another transaction reads a data item, it will produce no issue. So this also ends up with no issue. A transaction reads a data item after it is written by an uncommitted transaction. Whenever uncommitted happens and a write is involved, it will end up with error. So in this case we have uncommitted, but both the operations are read. But here we have one write and one uncommitted. Here we have one write and one uncommitted. So you can always have this clue. When there is a write operation involved and when there is an uncommitted transaction together in a scenario, this will end up with error. When it is a read operation or when it is committed transaction, we'll have no issue. So let's take the first case. If the transaction write commits, then read might get phantom tuple or unrepeatable error. Here there is no irrecoverable error. So obviously we know option 4 will be the right answer. This fourth statement will be giving irrecoverable error. Let's take 2 transactions T1, T2. Let's have a set of time here. We'll start with the data item A and read operation. There is a write operation to A and there is a read operation for A and read operation for B, write operation for B, then a read operation for B here. In the 7th time slot, it is getting commit here and the commit for T1 will be in 8th time slot. Now this T2 is actually reading updated value of A before the commit operation of T1. See here we have a read operation of A that will do no issue. I am writing the value of A. It means updating the value of A. So once I update A, the commit statement is occurring only in the 8th time slot. But before the commit happens, the uncommitted write, so written by an uncommitted transaction is this. The uncommitted write is read. R of A is given here. So T2 is reading the updated value of A from write of A. So here this situation is depicted in the diagram. The transaction T2 is reading a data item A after it is written by an uncommitted transaction T1. This is something like a dirty read. So this becomes the irrecoverable error. Next question. Given the basic ER diagram and relational model, which of the following is incorrect? ER diagram can have entities, relationship, and the attributes in the ER diagram will be represented using many symbols. In this case, ER attributes can be multi-valued. ER attributes can be composite. Multi-valued in the sense you can take if there are 2 or 3 phone numbers. So phone 1, phone 2, everything will be stored together. And if you take composite attributes, the example will be like address. So if you take address, it will be split into 3 other fields like door number, street name and city. So this is composite, and multi-valued is a single field having multiple values. Coming to the case of relational model, the attributes will have atomic value. This atomic value can be exactly one value belonging to a particular data type, or it can be of null value. Anyway, this null is also a single value given to that attribute. So let's check the statements now. An attribute of an entity can have more than one value. So entity is in the context of ER diagram. So it can have more than one value. It means it is multi-valued. So this is possible and one is marked as true. An attribute of an entity can be composite. Again, it belongs to ER context. This is also true as we saw here in the row of a relational table. So this is about relational model. An attribute can have more than one value. No, this is actually false because it can have only one value. It means it has atomic value. In a row of relational table, an attribute can have exactly one value or a null value. This is what we saw here. So this statement is also true. The only statement that is incorrect will be option number 3. So usually we know we convert ER diagrams to relational tables. So what will we do when ER has multi-valued attribute and when ER has composite attribute? What will happen in relational database? So when it is a multi-valued attribute, we just create a separate table to store those fields. Say for example, I can have the ID, I can store the phone numbers separately, phone 1, phone 2 as single attributes. Regarding composite, the parent will be lost and siblings are present. It means address will be removed. Instead, the number, the street name and the city will be included in the table. Here it is the parent and here these are the siblings. So in this case, this will be lost and this will be existing in relational table. Here multi-valued, it will have a new table along with the values. Even composite will have a new table, but their address field will not be existing. Instead, it will be with the sibling attributes as fields. Next question. The total cost of retrieving records in sorted order using an unclustered B plus tree. So they have given P denotes the average number of records per data page and N is equal to the number of data pages. So the total number of data records will be P into N or N into P. They have given F to be the ratio of the size of a data entry to the size of a data record. Here we have another count. Number of leaf pages in this tree will be F into N. So total cost will have the formula of F plus P into N. This will be the total cost of retrieving records in sorted order using unclustered B plus tree. So they say that F is usually less than or equal to 0.1 and P is greater than 10. Because F is going to be very small, this will not have any effect here. So P into N will be giving a good approximation. Option number 2 will be the right answer. Next question, matching list 1 with list 2. Actually, RAID belongs to unit 5, operating system topic, but RAID is also discussed in DBMS books and in some computer architecture books too. So for the purpose of keeping 10 questions in one unit, I have just kept RAID here in unit 4. Let's see what are the RAID levels. We have up to 6 levels: 0, 1, 2, 3, 4, 5, 6. 0th level, non-redundant stripping will happen. The first one will be with mirrored disks. Then the second one will have memory style error correcting codes. Third level will have bit interleaved parity. Fourth level will have block interleaved parity. Fifth level will have block interleaved distributed parity. And the sixth level will have P plus Q redundancy. The diagrams will be present in the books. You can have them for reference. Now we'll just map the options. Level 2, A will be mapping to memory style error correcting code. So it goes to error correcting parity. A will be mapping to 3. Option 1 and option 4 can be removed. Next, RAID level 4. It is block interleaved parity. B is mapping to 4. Option 3 is also ruled out. Option number 2 will be the right answer. Let's check C and D. RAID level 5 is about block interleaved distributed parity. So C is mapping to 2. And RAID level 3, it is bit interleaved parity. D is mapping to 1. With this, we are completing Unit 4 questions.